Okay, so support vector machines are really important, and what's amazing about them is that they're very effective, even though they are very simple. So let me, as usual, start with a new Google Colab. All right, and what we're going to do is we're going to do a classification task between 2 points that are just artificially created to generate some points with some dispersion and a gap between them. So we just make, they have standard deviation and centers and so on. It's just a function that creates random blobs. All right, it's got to import a bunch of libraries. This is using SecML, which we use for a lot of these more advanced projects because it includes a lot of the attacks against learning models in them, against machine learning. There we go. So you get this figure, and notice it's exactly equal to one I had here, because once again, we specified the seed for the random number generator up here at 999, and that means you get exactly the same pseudo-random numbers. So this, you want to separate the reds from the blues, and as you can see, you can do it with 100% precision, but you could do it with various lines. You could have a line that was nearly vertical right here, or you could have a line that was nearly horizontal here, or anything in between, and any of those lines would have 100% success at separating these two. So the solution is the scalar vector machine, support vector machine model is to choose the line that produces the widest road. And let me just get an image of this. Yeah, that's a good image for it. I thought I'd added one of these to the project. In fact, maybe I did. I wonder if I just need to refresh it or something. Anyway, this is what a support vector machine looks like. You a bunch of lines could do it, but you go for the line with the widest road. And for some reason, the actual Wikipedia, there it is. That's what I wanted you to see. So you choose the line that gives you the widest road between the three. And this has a bizarre effect. That road is defined by just these three instances, and none of the rest of the data matters at all. If you move or remove any of these dots or add more dots, it won't make any difference. So that is pretty strange, but it's true. And what's even more interesting is if you think about what we've done, if you have a fourth order polynomial function, you can just add a new parameter, which is the square, cube, and fourth power of an existing parameter. And now in a high dimensional space, that the separation border is a straight line or hyperplane. So since you can adjust the parameters and use combination parameters to add more dimensions, you can pretty easily create a space where the separation border is a straight line, and then you can just use this kind of support vector machine. So it is surprisingly effective. All right, so now we're going to create and train a model to classify these things. So we have pulled up a C classifier SVM for support vector machine, because this is one of the common important types of machine learning model. And the Python libraries are there, and there you have it. So there's the line that goes between them and is considered the best. Now, there is a strange limitation of this. You may remember in one of the previous projects, we talked about scaling the data. Like the data went from 0 to 255 for brightness, and we renormalized it to go from 0 to 1. You very often have to do that. If you do this, if you simply multiply the y-axis by 100, so it's exactly the same data, but instead this is 0, 1, this is 0, 100. Now if you create and train a support vector machine model, you're going to get a completely different solution. Remember last time, the optimal solution was this one. Now it's that one. Now, why is that? It's because it's minimizing, it's making the road as wide as possible, and the vertical distances count much more. So it's a huge horizontal distance corresponds to a small vertical distance. And so it's a thing to realize. If you scale things, you'll get a very different answer. These numbers are meaningful. They're not just arbitrary. If this scale is going up by hundreds and this scale is going up by ones, that is telling your machine learning model that precision along this axis is 100 times more important than precision along this axis. That a huge discrepancy here is acceptable, and even a tiny discrepancy up here is not acceptable. And maybe that's what you want, but if you're just feeding in data in whatever scale it came in without understanding this, you'll get the wrong answer because your data will be interpreted as more significant in one direction than the other when you don't mean that. Now, this, of course, is a ridiculous situation where you have a complete gap between the two pieces of data, so the actual machine learning classification task is trivial. A much more realistic situation is this one, where the data sets overlap. And therefore you cannot perfectly separate them. Okay, so now we just moved them and changed the standard deviation so these data sets overlap. So now there's a thing called linear support vector machine model where now you do allow some errors, and therefore it's not as simple as just the dots on the edge determining the model. You allow some penetration and parameters for that. And one of them is a smoothing parameter, CC, which is going to be important. Now, this is another important thing to understand about machine learning. Remember we said the problem is you don't want to overfit and just fit every random variation in the model. You want to fit the trend. Now, that's sort of a outside idea that we have. And so what you do is you add what's called regularization parameters to your machine learning model, which are parameters to force the answer to be smooth and not jerk around too much. And here, this is a regularization parameter C. So if C is 0.1, you get that. If C is 1, you get that. And looks like I didn't try their values just yet. All right. But this one, at 0.001, it should have failed. And I don't know why I didn't plot that one. It should have done 0.001. Maybe they're over to the side or something. Let's see. Oh, there they are. I just didn't scroll the right way. Okay. So with the regularization parameter this small, you get a terrible model where it just calls everything blue. And as you increase this regularization parameter, then it gets close to actually fitting. And when you get up to 0.01, it's doing a pretty good job, and 1.1 is doing a pretty good job, and 1 is doing a pretty good job. This is what you often have to do. You just move your regularization parameters through a range of values and see which one gives you a fit that you like. Which, like I say, it's machine learning is real. Machine intelligence, artificial intelligence is kind of overstating it. It's not that intelligent. It's not that far from the previous generation computers that just do exactly what you told them to do. It figures out a little bit of the problem, but not very much of it. So now let's try a data set that's curved. Here's one they call, I think, half moons or something. I think I'll make a new book for this. Move to trash, turn to Colab, new notebook. All right. So it uses another function called make moons just for this purpose to make useful data sets. So now we have blues and greens, and they can be separated, but not by a straight line. So we can create and train the model here. And this will show the pipeline that we're going to use. And this is going to add polynomial features. So we can have a polynomial curve in the decision line. This is what I was describing before. So what it's going to do is it's going to add features that are like x squared, x1 squared, and x2 squared, and perhaps even the cube. I forget how high the power goes. It's not obvious, but it's going to put those in. and then fit it in a higher order polynomial space so that you can fit a more complicated curve than a straight line, but it really is just a straight line in a higher dimensional parameter space. And so there you go. It can fit this shape to separate the two. That's the decision function. All right. And there is something else called a polynomial kernel, which is a mathematical trick to do this much more quickly in computation and end up with essentially the same thing. And you can vary the degree. So that's the support vector machines. Let's stop this one.